Let me get my mic. Okay. All right, students, get your eye clickers out. We're going to be doing a little bit of clicking together, and we're going to do some scientific notation at the wazoo today. Mainly because we're going to be doing some calculations with Planck's constant. And there's no other way to deal with Planck's constant than scientific notation. And that brings to mind the final exam. We'll be down the hall in room 201 on Saturday, December 10th at 1 o'clock. Be there. And bring your eye clicker, because we're going to have, just think of the last midterm. It's going to be double the size of that. It's 100 points. So think of, twice as many calculations in the clicker part. So you're going to need your eye clicker. All right? And we're going to do it, it's going to be in self-paced mode, so it won't be such a pain in the you-know-what as exam 3, but definitely bring your eye clicker, and that'll be good. By the way, I set up a new row in the grades page for SSG bonus points. You may have noticed it. I haven't put it in for anybody, but I will be. Hopefully this weekend I'll get to that and not be such a slacker. Okay, so here's our big thing. We're going to do some calculations, and there'll be a talking PDF about phase space and quantization of phase space. Homework 16, I'll activate that tonight sometime, maybe after supper or maybe first thing in the morning. So you'll have the whole weekend to work on that. Now, last time we talked about the spectrum of hydrogen and how the mysterious disappearance of most of the Roy G. Biv colors was explained by de Broglie as saying, well, if the electron has wave properties, then the only way that you're going to get an electron on an orbit is with constructive interference. A wave, if you think of it as a wave, it's going to be discombobulated unless it's exactly the right wavelength, exactly the right size, exactly the right energy and momentum, and then changing the photons are going to be exchange energy between the different quantized energy levels. Excuse me. The other thing that we talked about last time, we alluded to a second way of understanding quantization in an abstract space, phase space we call it, where momentum is usually charted on the vertical scale and position, the coordinate position on the horizontal scale. We'll talk a little bit about that again today at the end of class. Now, first thing we're going to do today is calculate the nitty-gritty of the de Broglie wavelength. And we're going to use some of the physical constants. Here's a little slice, a screen grab from a publication on a website down in Stanford. They keep track of all the constants of nature, the latest experiments, latest measurements, the best values. And we're going to be using speed of light, Planck's constant, and the mass of the electron, the mass of the proton today. So let's talk about a proton. So let's work with, and get your clicker ready because you're going to have a multiple choice clicker question in just a second. Proton mass, the mass is 1.673 times 10 to the minus 27 kilograms. A kilogram is a normal size unit of mass for everyday objects like humans, bicycles, cheeseburgers. Well, a fraction of a kilogram for a cheeseburger. Unless you got, whoa, can you imagine a cheeseburger? Well, it'd have to be a steak. You could have a 1 kilogram steak. That'd be a big steak, boy. But anyways, kilograms, everyday objects like things that we eat, things that we ride, things that we are, we're humans, things that we see, mountains. But for protons, no. 10 to the minus 27 kilograms, very, very teeny fraction. I don't even know what that is. Let me think. 10 to the 3, 1,000. 10 to the 6, a million. 10 to the 9, a billion. 10 to the 12, trillion. 10 to the 15, quadrillion. 10 to the 18, 5-otillion. 10 to the 21, 6-otillion. 10 to the 24, heptillion, I think it's called. 10 to the 27, octillion. So it's an octillionth of a kilogram for a proton. But we're going to think of it as moving at 5% of the speed of light. Now, we can do this easily in the lab in this day. 100 years ago, it would have been tough to get something up to the speed of light. But 5%, yeah, we can do that. It's not hard. And that's about 0.15 times 10 to the 8 meters per second. Now, I'm going to ask you in a second here to calculate that. All right, so let's compute the proton momentum. And I'll ask you to answer the following question. All right, A, B, C, or D. And go ahead and compute, and go ahead and turn them all on. And you can look at the numbers there. Hopefully you already wrote them down. And just talk with your neighbor if you need to. Interesting. Boy, that was refreshing. Did you text that to Derry yet? Good. Good.
Yeah.
Hope she feels better.
I know.
But of course, it's even worse if you get sick during finals week.
Oh my, because you have to go.
30 seconds. Yeah, man, because if you get sick during finals week, that means you're going to a final and you feel like sick as a dog.
Yeah.
That's no good. So hopefully her immune system will be impervious by exam week. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Presentation mode. Okay, raise your hand if you got this correct answer. It looks like a bunch of you voted for C. Raise your hand if you voted for C. Yeah, you guys are correct too. And hey, you guys. Yeah, a little psych out version there. But the reason I put the two different versions of correct answer is so that you can write both of them down, and then you just in case you're a little bit rusty with scientific notation, and you're trying to figure out, okay, how do I do this in scientific notation? Here's a pair of numbers. They're both right. They're both correct, but they're expressed slightly differently. Now, supposedly, scientific notation is not complete if you have a 0 point something, or if you have more than 9, if you have a 10 point something times some power. But, I'm a physicist. I'm not a mathematician, so I don't mind either of these two answers. So it's a good thing to refer to. And second note to everyone, what I say to one, I say to all, and that is a proton with about 10 to the minus 20th kilogram meter per second of momentum. That's not bad. That's an everyday proton. That's normal momentum state for a proton. So make a note of that. It seems small to us, but for a proton, yeah, 5% of the speed of light, not a problem. We can do that in the lab, you know. Not at the drop of a hat, but almost as easy as dropping a hat. Okay, and so we're going to be doing some more momentum calculations here. Excuse me. Oh, that's what always happens when I drink soda pop. I always burp. Anyways, 10 to the minus 20 kilogram meters per second is a good range. Now, let's calculate together the de Broglie wavelength of that momentum, or excuse me, of that proton at that momentum. And I'm using 2.5095 times 10 to the minus 20. You go ahead and jot that down if you like. And what we're going to do is slip that into the de Broglie relation. So here's the de Broglie relation up here in the upper right. And Planck's constant, we already know what that is, 6.6 blah, 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 times 10 to the minus 34. And then we're going to put the P in the denominator. Here it is. And I'm using 6 significant figures for Planck's constant and 5 for the momentum. So 6.62607 times 10 to the minus 34. And notice, my wonderful students, Planck's constant is a joule second. But here I'm expressing a joule second as a kilogram meter squared per second, because I want to do some cancellations. All right? And in this form, you can cancel fairly nicely. And we'll do that in just a second. Matter of fact, let me move all this up a little bit. And all right, so here's my quotient, and here's my kilogram meter squared per second. And first thing I'm going to do, I'm going to cancel kilograms. Ching! So go ahead and cancel those babies out. And that second or per second up here in the numerator and a per second in the denominator, bing, they're out of here. All right. So my secret technique of turning a joule second into a kilogram meter squared per second is nice. And look, I've got meter squared on top, meter in the denominator. So I cancel the meter in the denominator and one of the powers of meter in the numerator. I still have one though. Okay, so I've still got meters in the numerator for units. And that's good. What's your name again? Yeah. No, not you. You with the specs. Jessica what? Jessica what? Tyson, right. You were up talking to me at the beginning of class, so that's why you caught my eye. Jessica and everyone. We want meters. We don't want to cancel everything out because wavelength is measured in meters. So that's where we're going to get here. Now, the other thing that we got is a 10 of them, and make a note of this, put a circle around it or something. 10 to the minus 20 in the denominator is the same as 10 to the regular 20 in the numerator. So my numerator is really 10 to the minus 34 and a 10 to the regular 20. So that's really a 10 to the minus 14 in the numerator. There we go. So here it is, 10 to the minus 14. And the only remaining unit is meters. And then my quotient, 6.62607 divided by 2.5095. Now that's going to be 2 point something. So I had 2 point something times 10 to the minus 14. This is what it works out to. And I'm going to ask you to do a calculation just like this on the iClicker in just a minute. Right? We're going to do 2 of them together. So let me pause now for a question. Anything you want me to review? Yes. M equals, you mean this right here? Well, that's meters. This is 10 to the minus 14. This is the remaining meters. See, it's down. That's my, yeah, it's still lambda. So lambda here and the equal sign. So I just didn't write lambda down here. I could have. All right. Question over here. Yeah. This, where did I get that? I got that by looking it up in the particle data group website down at Stanford. That's Planck's constant. That's 6 significant figures, 10 to the minus 34 joule seconds. And hey, you guys, on the exam and on the homework, don't expect, I don't expect you to memorize Planck's constant. I don't have it memorized. I don't use it that much. Because believe it or not, in my branch of theoretical astrophysics, theory of relativity, we use a version of Planck's constant that's equal to 1. So it's extremely, so we, it's, I hardly ever use the real Planck's constant. But this is what it is. All right, so does that answer your question? Good, all right. Another question. Your calculational lives depend on this calculation. All right, comment. 10 to the minus 14 meters is way smaller than an X-ray wavelength. X-ray wavelengths are maybe a few nanometers down to maybe a few hundredths of a nanometer, a few 0.01s of a nanometer. Okay, visible is a few hundred, from 400 to 700 nanometers for visible light. And ultraviolet is from about 400 down to a few nanometers. And then a few nanometers down to 0.01 nanometers for X-ray. And infrared is above 700. And radio wavelength above 700 nanometers. A proton at 5% of the speed of light we can easily do in a lab. For instance, and this is my second note based on this first side note. Second note is, down at Orlando Regional, they have a new machine down there called a proton accelerator. They use it with accelerated protons to zap cancer cells. Now, if you've ever known anybody that had cancer, one of the ways that they try to attack the cancer and kill it is with X-rays, right? And that it's extremely punishing to take a lot of X-rays. Now, I've never had that many X-rays myself, but I've had acquaintances and family members that have. It is not fun. The proton is even more penetrating. It has a smaller wavelength. It can zip right through atoms, between atoms, like you dashing between buildings here at UCF. No problem. X-rays, not quite as easy. All right, so proton waves with the proton accelerator downtown at Orlando Regional, I think they call it proton therapy instead of radiation therapy. They're using de Broglie wavelength protons, maybe about this, maybe a little bit slower, maybe not 5% of the speed of light. But 5% of the speed of light is fairly easy to do with protons. And so, they may use 1% or even 0.1% of the speed of light, and they're still going to have nice tight wavelengths, good penetrating, and apparently it's easier on you. And it's more accurate and a little bit easier to take. Okay, so don't Don't ever think, that no useful information ever comes out of Physical Science 1121. All right, here we go. Let's try some calculations. I'm going to turn you loose. Here's number 1, electron. And I'm giving you the momentum state, 2.65 times 10 to the minus 23 kilogram meter per second. Hey, there's Planck's constant. H equals 6.63 times 10 to the minus 34. Don't mess up the exponent. I saw a student after class just now, and he said, Dr. B, where did I make an error? And he had Planck's constant 10 to the minus 14 instead of 10 to the minus 34. So, all right, so go ahead to all on and go ahead and start your question. And hit the send key as soon as you have your answer in there. All right, to the nearest tenth of a nanometer. Yeah, that's good. They can read all of that. And we'll give you a few minutes for that. Also, section 2. Oops. I messed it up. I guess it's all right. See all these things.
Mhm.
These are like controls.
That's so cool.
Yeah, it's kind of neat. Home page. I don't use this notebook. You can even do Wi-Fi for this. If you have, I don't think this pen has Wi-Fi, but some of them do, so you can do all this stuff. See, Facebook,
Yeah.
Dropbox, Google Drive.
Wow.
Yeah.
That is so
This
cool.
is that's the next pen up from this.
Yeah.
Mm-hmm.
Oh my gosh.
What?
What is happening? I went to look at that. Look at all this.
Mm. One minute. How many answers do we have? That's pretty good.
143, yeah.
Yeah, we'll give them a minute. We're doing good.
Another one.
I wonder where this guy is.
I know.
Can you take this over? Are you heading over towards the student
I'm
union?
not, because I have my interview at 1:30, so I
Ooh,
gotta dash
so
out
that
of
means
here.
Dr. B, I have to take it over there.
Yeah,
All right, that's
I
all
would.
right. I know normally you would do that.
I might leave a couple minutes early too, just to make
I
sure.
might have to slack off and go over there. Gosh. But that would be all right because then I could get another monster.
There you go.
Actually, I don't want to take too many monsters because I might start getting a little jittery.
Yeah, on Monday at my internship, one of the interns, she had coffee. No, she had a monster and then she had coffee. Because she works at night at
So she's
Orlando
like-
Health. And so
She's up for
and we
40
didn't do a lot
days and
that
40
day,
nights.
So we had nothing to do. So she was sitting there bouncing because we had nothing to do. And I was like, oh my goodness.
No. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, looks like about 71% of you got 0.025. Can you do the presentation mode? So that's good. Let's review the calculation. If you got it wrong, you could jot this down. All right, here's your setup. Planck's constant in the numerator. And the momentum state, 2.65 times 10 to the minus 23. And this is a normal bit of momentum for an electron. Electrons have about 1/2000th of the mass of a proton. So instead of 10 to the minus 20, it's down in the 10 to the minus 23s. All right. Now that 10 to the minus 23 in the denominator, you can park that up on the numerator. In case you're wondering why I was talking about, yeah, that's the same thing. Take it out of the denominator, park it upstairs in the numerator. Ching! But make sure it's a 10 to the positive 23 up in the numerator. And then you've got a 10 to the minus 34. And girls, please, don't talk over the top of me. I've had to yell at you guys over there a couple times this semester. Don't do that. All right? There's other people studying next to you, around you, and they're trying to work their boop off to get a good grade or even a passing grade. All right? So if you don't care about your grades, they do. So please respect that. All right. The other thing I want to do, of course, is my standard Dr. B trick. Change that joule seconds into kilogram meters squared per second. All right, there we go. Got that. And then I do some cancellation. And so I'm canceling kilograms and everything. And so I have 6.63 divided by 2.65. Hey, you guys, you can do that on paper and pencil. 6th grade style, long division. On exam, on the final, if you have to. So if you loan your calculator and it doesn't come back to you, for the final, you can do it on pencil and paper. We're going to have plenty of time for the final. Twice as long of an exam, but you have 3 times as much time to do it. So time pressure is not an issue. This is how you do it on pencil and paper if you don't have a calculator. All right? And so there's your answer, 6.63 divided by 2.65, and then times 10 to the minus 11. And the answer is in meters. All right, Chelsea? Basic. All right, so 2.502 times 10 to the minus 11 meters. Hey, you guys, is that smaller or bigger than a nanometer? Yeah, it's smaller. Because a nanometer is 10 to the minus 9 meters, and this is 100 times smaller. Okay, but 0.025 nanometers, that's on the order of an atom, maybe a smallish atom. Some atoms are bigger than others. And so my comment to you is an electron at this momentum going through an atom or a crystal lattice composed of many atoms is going to diffract. And that is what Davison and Germer observed, and many, many people after that. All right? So an electron in this momentum state, make a note of it, in an atomic system will diffract. Now, if you send an electron in this momentum state through that door in the back out into the hallway, forget about it. That door's so big, it's just going to zip all through as if it were a particle. It's not going to diffract at all. So the aperture or the slits that it goes through as a wave, they've got to be about the same size. Maybe a little bit bigger, maybe a little bit smaller. But if they're way bigger, you're not going to get any diffraction. So that door's so much bigger, then this wavelength, that door back there, no diffraction. Atomic crystals, plenty of diffraction. Jessica, question. No, I'm always going to move it over to whatever Dr. B says. If I ask, I mean, if you go back and look here, let's go back and look at the actual question. See, I always give you an example, and especially with scientific. If I have to set up the software to take a certain amount, a certain answer, whatever the round off value is that I choose. I will always tell you that, and in this case, I'll give you an example of converting something times 10 to the minus 11 into a nanometer, a fraction of a nanometer, okay? So I'll always give you that, but it's not always subtract 3 decimal points or, whatever. It's always whatever I tell you, and I'll always try to give you a good example that you kind of work it out. And it won't be the answer, but if you get, on your calculator, 4.89 and then a little teeny 11, minus 11, is how that would show up if you did it on your calculator. And then you say, okay, so that's 4.89 times 10 to the minus 11. And Dr. B says that that's 0.049, so I'll type that in. All right, so I'll always give you that prompt so that you can kind of work it out. Because I don't want you guys to, I want you to think. I don't want you to fool around with, the math department. I mean, much as I love the math department, it's not a math class. All right. So let's get back to this. All right, so there's my calculation. La, 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 la. Now, as I said, an electron going through a crystal lattice at this momentum state, plenty of diffraction. An electron going through that doorway or going up your nose at this momentum state, no diffraction. But how about this? How about an everyday object, a paperclip? Paperclip is usually about 1 gram, so let's work out this problem. Here we go, calculation number 2. And this is going to be way different, and I'm going to ask you to answer in scientific notation. So hit the refresh button and get ready for this question. Paperclip, the mass is a gram. So if you're going 2.65 meters per second, your momentum is 2.65 times 10 to the minus 3 kilogram meters per second. All right? Calculate its wavelength. All right? And if you get something times 10 to the minus 11, type it in as 1.81, for instance, and then the letter E, and then minus 11. And by the way, turn on the lights. When you're on this, Jessica and everyone, be careful. The equal sign looks a lot like the minus sign. So, all right. I have spaces, but you don't have to put spaces in. So you can just type in an E and then a minus 11. All right. I did it so that you could tell them apart. All right. All right. So, Molly, if you want to do it in scientific calculation on your calculator, this one's for practicing that. Good. I see a lot of you guys kind of working, interacting. Boy, I don't like hearing that. Who is it over there that's coughing? Gosh, that's Tuesday you were coughing too. What do you have, bronchitis or something? Man, I hate hearing that. It's because it sounds really bad. Have you gone to the doctor? Why not? Do you live in the dorms or something? Are you like a freshman? Look, I'm not really laughing because you're freshmen. Freshmen's first semester here. A lot of times they crash and burn finals week because they're so stressed out and tired that they get sick, and you're already sick. So you better get over it before finals week, my friend, or you're going to crash and burn. Because it's seriously. I mean, you sound bad. I'm not criticizing you, but I'm telling you, it does sound. So somebody else has got it.
Yeah, I see you. Because it doesn't let you go over it to get rid of them.
See, now drinking water is how you avoid getting that kind of stuff. Seriously. Stay hydrated up. I had a friend when he was an undergraduate, he ended up in the emergency room. He collapsed. He woke up in the emergency room. You know why? He was dehydrated.
I know the answer.
Yeah.
And final exam week. So some people get sick. My buddy, he got dehydrated, ended up in the ER.
We have an emergency.
Yeah.
So his clicker is being really weird, and it's putting decimal points. But I went and tried to get rid of them, move the thing over, and it won't let you get rid of them.
Yeah. Come
I
here.
have the thing though.
Let's see what you got. 2.50.
To the negative 30 first.
Is that what it is? Let's turn it off. Let's try to reacquire. Okay, go nitro.
True.
Okay. Yeah, so this is short answer. So you have ABC. And so let's see if I could do it. All right, now the decimal is down there.
Yeah. I got the first one, and it was give me more for some reason.
Yeah.
Okay.
Your decimal went away. See?
It did?
Yeah, you see, it's not there anymore. You see that?
Yeah, let me see if I can.
I don't think you have to put the 0, right?
What do I want? 3 significant. What do you? Yeah, we'll put in a 0. Yeah, we'll put a 0. Let's go up and get an E. Okay, now what's your?
Negative to the 31st.
Okay. Where's the minus sign?
I have no idea.
Probably somewhere around the decimal, I would think.
Maybe. Oh, wait. No.
That's to the. That's a underscore. That's an equal. There's your minus sign.
I bet.
Okay.
Yeah.
Let's go back up and get that.
I guess you don't want to.
Code,
Yeah. True. I guess you don't want to say it all.
Yeah.
Yeah, I think it's
Yeah,
good
because
now.
you're on.
Yeah,
You're on
true.
mic.
All right. Such a long
Ding.
answer. Sweet.
All right.
Yep.
All right. 30 seconds.
Oh, man. Whew.
Are you up for dismissing early today? You think? Maybe? Please? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1,000. 1, 0. Okay, good. I was thinking about something. Presentation mode, please. You know what? I got somebody that typed in an answer here that looks good, but they have 6 zeros. And that's not good. Raise your hand if you got 2.5 E minus 31. You know, and I don't see a whole lot of those. I know one guy definitely got it because I typed it in for him because he was having troubles. But there's some people with spaces. Yeah, okay, there's a good bunch here. Now, when I grade this, I'm going to be pretty generous and stuff. But you definitely want to make sure you know how to handle scientific notation for the final. Okay, comments on this calculation. We're not just doing it to calculate. The reason that we did the paper clip is to show that the lambda for the paper clip at this momentum state is extremely small. 10 to the minus 31 meters, forget about it. I don't care what object you have, the smallest nucleus, this is smaller than that. So this thing is going to zap through. The problem is, it's a paper clip, so it's got a large size as well. So very small wavelength. Now what that means is, it would require, to see the diffraction of a paper clip, it would require something approximately 10 to the minus 31 meters in size. There's nothing in the universe that has that size. It's too small. That doorway at the back, you're not ever going to see any diffraction out that doorway or even out of your pocket. It is many powers of 10 smaller than your pocket. So make a note of that. Everyday gap that might produce some diffraction, it depends on the wavelength going through the gap. Your pocket being the gap, a few inches, the wavelength being 10 to the minus 31 meters, forget about it. It's too small. It's going to zap through just like a particle, and that is what we observe. We observe paper clips basically acting like particles. You know, you throw it through the air, it has a very well-defined position, it never diffracts anywhere. Okay? So diffraction effects, my third comment here. So first one is on top, then the yellow comment. And the third side note is, everyday objects have so much momentum and such a small wavelength, we never see diffraction. So your left earlobe theoretically has wave properties. Your big toe on your right foot has wave properties, but the wavelengths are so small, we never observe any wave effects. Right? Now, fourth note is that this is where Planck's constant rules all. Planck's constant is really small. And therefore, only the smallest things like electrons and protons exhibit wave properties. Planck's constant is really small. So if you have a big momentum state in the denominator, you're going to have an extremely small wavelength. And so you're not going to get diffraction effects. So Planck's constant rules all of that. That's it. I mean, MV, you can figure out a momentum state for a paperclip, no problem. You can figure out a momentum state for a proton, no problem. It's Planck's constant that determines whether you see wave effects or not. And for the value of Planck's constant in our universe, 6.63 times 10 to the minus 34, only electrons and protons, molecules, stuff on that, or even amoebas. You know, viruses and amoebas and stuff, some blood cells, they're classical. They do not exhibit wave effects. Only the very, very smallest. Now, I'm going to show you something on, can you go to document cam, please? I made a talking PDF that worked out a real life example down here of an oscillator system that shows how the change between dynamical states in bundles of Planck's constant, as I mentioned before, leads to quantization of the system. Now, I've already recorded this, and being as how it's Thursday, and being as how you guys would like to dismiss early, I'll let you listen to this one. I'll post it later this afternoon, and you can listen to it on your own. So, you're dismissed now early. Homework 16 will activate. Plenty of calculations tonight or maybe tomorrow morning. Jessica? Morgan? Mm-hmm. Yeah, it's just, I was just doing it with another student. Okay, you go up and get, well, let's see, let's delete here. Okay, so oh, I see you have your decimal point in there. Okay, let's put that back. 0. Wait a minute. And then you go over, and then you go up and get an E. Okay, so this, see this symbol there? Yeah, that's what you do. That's what you. No, you don't use this one. No, use it's up here, above the numbers where the letters are. Okay. There you go. And then you go over here. Then you go back down and get the minus sign. That's down below the numbers.
Do you have their exam printouts?
Okay. Yeah. Section 2 is one of those. Okay, and then you do this. So there's the, see that? This is the equal sign.
Oh, wow.
Yeah, it's nasty. So, but this is the minus sign. Okay. Wait a minute, that's the division sign. No, that's the minus sign. Okay. And then you go next. Then, so that's the minus sign. And you go up again and get a 3. And then you go over and get a 1.
C-A-R?
And then you send it.
C-O-R-R.
Okay. Now we're off the system now, but anyways, that's how you do it.
Okay.
Good. You are welcome.
I have a blank on this. I just want to
Okay.
Stefan S.T.
Sadaf Lolani. In my Hall of Fame. I'll check your Scantron next week probably.
Okay, that's fine.
Yeah, one blank.
Is this just
And
for
it may actually be a blank.
Yeah, that's what I don't
So
know.
if it is, your grade won't change. But if it's not, and just a really light dot, I'll be able to tell that by looking at it.
Okay, so you
And so but if it is a really light dot, it might still be wrong, and then it won't be any change. But if it's a really light dot and correct, you'll go up by 1.
Okay, thank you.
And I'll do it in web courses,
Okay.
and then you'll be able to pick this up maybe Tuesday. Yep, you too.
For one of the problems,
I think he said December
you explained how that was a diffraction point of that material. So
Have a good one.
you too.
Wait a minute, hold on. I think I'm still recording.